Hello everyone. In this video we will discuss about the optical fibers and its types. Then we will also talk about the acceptance angle, numerical aperture and maximum incident angle. And we will try to solve some numericals as well. So let's start with the basic idea of optical fiber. Optical fiber refers to the technology and the method for transmitting data as light pulses along a glass or also made up of plastic fiber. And these fiber optic cables are used for long distance and high performance data networking. They are capable of transmitting data over longer distances and at higher bandwidths than electrical cables, making them a critical component in modern telecommunications, internet and computer networking. So this is the basic idea of optical fiber. We have a number of applications. The major application in telecommunication, internet and computer networking, and they are very different from the electrical cables. In electrical cables, the data transfer is in the form of electricity, but in case of optical fiber, they will transmit data in the form of light. So about the major components of optical fiber, the main components includes core, cladding and buffer jacket. Now what is core? Core is the central tube of very thin size made up of optically transparent dielectric medium and carries the light transmitter to receiver, and the core diameter may vary from micron to 100 micron, right? So this is the size of core, and this core is used to transmit the light. So from here light is only propagating through our core. And what about cladding? So second main component is cladding, and it is a outer jacket material surrounded the core, having a reflective index lower than the core, and cladding helps to keep the light within the core throughout the phenomenon of total internal reflection. Okay, so through this total internal reflection, cladding will help this light to keep within core. Now third main component is the wafer jacket. Buffer jacket, it is a plastic coating that protects the fiber made up of silicon rubber. The typical diameter of the fiber along the coating is 250 to 300 micron. So this is the size of buffer jacket. Now let's talk about the types of optical fiber. Now we have basic idea. We know the application of optical fiber. We know the basic components of optical fiber. So let's try to differentiate these optical fiber and how many types of these optical fiber we have. So optical fibers are categorized in two manner. One based on the number of modes, and second one is the based on refractive index. Okay, and again based on number of modes, we have two types of optical fiber: single mode optical fiber, multi-mode optical fiber. And again in on the basis of refractive index, there are two types: step index optical fiber and graded index optical fiber. Right, now let's talk about the single mode optical fiber. So in case of single mode optical fiber, only one type of ray or light can propagate through the fiber. Okay, and this type of fiber has a very small core, and the diameter of this core is approximate 5 micron, and the diameter of cladding is very high, which is 70 micron, and we are talking about the single mode optical fiber. Okay, so the core is approximate 5 micron and cladding is approximate 7 micron, right? And the difference between the refractive index of core and cladding is very small. It means mu1 and mu2, the refractive index of core and cladding is very small for single mode optical fiber, right? There is and also there is no dispersion, that is no degradation of signal during the traveling through the fiber, and this type of optical fiber is used to transmit the signal for the longer range due to their approximate no dispersion, and due to which there is no degradation in the signal we are having, right? Okay, so this is about single mode optical fiber. If we want to draw the diagram of single mode optical fiber, it is this is core, okay, and this is cladding, core cladding, and then you have axis of optical fiber, light is transmitting through within optical fiber. Single mode, only one ray of light can propagate through this optical fiber. So you can draw this diagram during answering or when you are writing answer for the single mode optical fiber, right? Now let's talk about the multi-mode optical fiber. So in case of multi-mode optical fiber allows many modes for the light travel through optical fiber, and the core diameter is approximate 40 micron, and the cladding is again 70 micron. No, due to its high diameter of core as compared to the single mode optical fiber, this type of optical fiber allows multiple rays of light that can travel through it, okay, and the relative refractive index difference is also greater. So it means this mu2 is also greater. The nu is also greater in case of multimode optical fiber, and there is signal degradation due to multimode dispersion. So as we are using multiple mode for the transmission, then these multi-mode will also give us a dispersion, and it is not suitable for long distance communication due to large dispersion and attenuation of the signal, right? And there are two categories based on multimode optical fiber. Now again, this multimode fiber is of two types. First one is a step index optical fiber, and then graded index multimode optical fiber. So these multimode are again differentiated into two types. One is the step index multimode optical fiber and graded index multimode optical fiber, right? So we will talk about this one in case of refractive index. One second category of optical fiber is based on the refractive indices, and first of them is step index optical fiber. So the refractive index of the core is constant in case of step index optical fiber, and this is the schematic representation of step index optical fiber. The refractive index of core is constant, and for cladding again refractive index is constant. It means we have constant refractive indices for core and cladding, okay. So the refractive index of core and cladding is constant if light is traveling from core towards cladding. In this type of optical fiber, light will experience a step in refractive index. It means refractive index is suddenly going to change, and throughout core and cladding the refractive index is constant, right? Step index optical fiber. And in case of graded index optical fibers, so graded index optical fibers are such kind of fiber in which core has a non-uniform refractive index. Let's say I'm going to draw a core, and this is the center of core. Let's say this is our core, and the center of core is this one. So when light is traveling from center of this core towards the surface of this core, the refractive index is not constant. The refractive index is getting decreased in case of multimode optical fiber. Again, I'm repeating this. In case of graded index optical fiber, the core has non-uniform refractive index, and that gradually decreases from the center towards the core cladding interface. This is the core cladding interface, and at this point, the refractive index is gradually decreasing, right? And the cladding has the uniform refractive index, and your cladding, if this is the cladding of optical fiber, it is having a uniform refractive, okay, and the light rays propagate through it in the form of skew rays, okay. So having a non-uniform refractive index. So when light is traveling from core towards cladding, light is itself reflecting towards core due to change in refractive index, and at this core cladding interface it will experience very change in refractive index, and then light will bend towards the core again, and you will get a TIR, okay. So this is about the types of optical fiber. So now let's talk about the acceptance angle for the optical fiber, because we need total internal reflection. So there must be some suitable angle through which we can enter light through the optical fiber, and we will get total internal reflection. So we are having a concept of acceptance angle, and how to find out. So here's the diagram of the optical fiber, and we have this diagram having core and cladding, and the refractive index of core is mu1, and the refractive index of cladding is mu2. and the condition is that mu1 is greater than mu2. mu1 greater than mu2, and the refractive index of the medium from light is entering, so light is entering from this medium, and the refractive index of this medium is mu naught. Okay, so this is the conditions we are taking these conditions, and the light enters in the fiber at an angle theta I, okay, with the axis of fiber. The wave gets refracted at an angle theta r and strikes at core cladding interface at point B with an angle theta. If theta is greater than critical angle, that is theta c, if this theta is going to greater than critical angle, that is theta c, the wave undergoes total internal reflection at the interface. Okay, so then and only then we will get total internal reflection if this theta is greater than critical angle. Okay, so as long as theta is greater than critical angle, the light will stay within the core of the fiber and we will get total internal reflection. So let's compute the incident angle theta I. Okay, so at this point A, let's apply the Snell's law. Apply. At point A, so what we are getting? We are getting sine of theta I over sine of theta r is equals to mu1 over mu naught, right? And I am giving this equation number 1. So largest value of theta I is only when theta is equal or greater than theta c, that is critical angle. Then this value of incident angle can be represented by theta I max or not. Okay, what I am saying here, incident angle is only suitable, this incident angle is only suitable when theta is equal or greater than theta c. Am I right? Okay, and let's say we will call this theta I, that this is the maximum incident angle through which we are getting TIR. If we change this incident angle, if we decrease this incident angle or increase this incident angle, this condition will be affected. We will not able to get theta greater than critical angle. Then light will escape towards the cladding. So what I am saying, that I am going to take this theta I as a theta I max, right? So here we can write that theta I max sine theta I max, right, over sine of theta r is equals to mu1 over mu naught, and let's say let's find out sine of theta I max from here is equals to mu1 over mu naught sine of theta r, and by using this triangle ABC we can find out sine of theta r. So theta r is equals to sine of 90 minus theta, is it? So this will become mu1 over mu naught cos of theta, right? And we are finding sine theta I maximum. So here again, if this theta is equals to critical angle, so can I write theta is equals to theta c sine theta I max is equals to mu1 over mu naught cos of theta c, right? And this is my equation number 2. Okay, now at critical angle theta c, now let's apply Snell's law at this point B. So what we are getting, so by apply Snell's law at point D, so what we are getting, sine of theta c over sine of theta is equals to mu2 over mu1, and here this theta is equals to 90 degree, so sine theta will become 1, and we are only get with sine of theta c is equals to mu 2 over mu 1, and use now here use a property, that is sine square theta c plus cos square theta c is equals to 1, and cos square theta c is equals to 1 minus sine square theta c, right? And cos of theta c is equals to 1 minus sine square theta c under root, and this sine of theta c is equals to 1 minus mu 2 over mu 1 square under root. Okay, and from here we can find out mu 1 minus mu 2 square, mu 1 square minus mu 2 square over mu 1 square under root, and this is the value of cos of theta c. I am calling this as equation number 3. Okay, now what I am going to do is to put this cos theta in my equation number 2. So put equation 3 in equation number 2. What we are getting? So we are getting sine theta I maximum is equals to mu 1 mu naught mu 1 square minus mu 2 square under root mu 1 square, right? And I am taking this mu 1 outside, so mu 1 over mu naught mu 1 square mu 2 square under root, these are going to be cancelled out, and we are getting mu 1 square minus mu 2 square under root over mu naught, right? Okay, and this is the value of sine of theta I maximum. So here we are having this sine of theta I maximum, and this is the maximum incident angle through which we can enter the light and getting total internal reflection. So can we call this maximum angle as a acceptance angle? Yes. So this sine of theta I maximum is equals to acceptance angle, right? So sine of acceptance angle is equals to mu 1 square minus mu 2 square under root over mu naught. Okay, so if the incident light is entering from the air medium, let's say this mu naught, let's say this light is entering within optical fiber from air medium, so this mu naught is equals to 1 in this case, and sine of acceptance angle will become mu 1 square minus mu 2 square under root, and acceptance angle is equals to sine inverse mu 1 square minus mu 2 square under root, and this is the expression to find for acceptance angle. And from here you will get number of numericals. You just need to put the value of refractive indices of core and cladding and take sine inverse of that. You can find out acceptance angle. So theta A will be the acceptance angle. Here theta A is equals to acceptance angle. Now another very important topic is numerical aperture. Numerical aperture, right? Again, numerical aperture is a parameter that is the most important parameter of the optical fiber, and it is a measure of, so it is a measure of how much light can be collected by an optical fiber, okay, or also defined as light gathering capability of an optical fiber, okay, and it is defined as, and this numerical aperture is represented by an A, and it is defined as, so numerical aperture is defined as sine of acceptance angle. and the acceptance angle we have just figured out. And this will give you numerical aperture is equals to sine of acceptance angle is equals to sine inverse mu1 square minus mu2 square under root. And here sine inverse and sine is going to be cancelled out. Numerical aperture will be n1 square minus n2 square under root. Okay. So this is the numerical aperture, the value of numerical aperture. Okay. Now, as we are defining numerical aperture is sine of acceptance angle. So the maximum value of numerical aperture is 1. Right. Okay. So can we write here numerical aperture is equals to mu1 square and this mu1 square minus mu2 square. So we have a square minus b square is equals to a plus b into a minus b under root, right? And also we know the fractional refractive index, that is delta mu is equals to mu1 minus mu2 over mu1. This is the formula to find out fractional refractive index, and from here we can find out mu1 minus mu2 is equals to delta mu1. Okay, so this is represented by delta mu1, and if mu1 is approximately equal to mu2, then we will get mu1 plus mu2 is equals to 2 mu1, and then numerical aperture is equals to 2 delta mu1 square under root, and can be written at mu1 to delta, and delta is the fractional refractive index. So this is how you can modify your equation, and this is all about the optical fiber, acceptance angle and numerical aperture. So I hope you like this video. Thank you so much for watching this video. Thank you.